Non-electrical characterization. At NanoSurf, we have identified the 6 mainstream nanoelectrical AFM modes. The Kelvin probe force microscopy or KPFM, which measures surface potential, the conducting AFM or CAFM that measures local sample resistance, the piezoelectric force microscopy or PFM that measures piezoelectric response to the voltages applied between the tip and the sample, the magnetic force microscopy or MFM, which images stray magnetic fields above the sample, the scanning microwave microscopy or SECM, which measures electromagnetic impedance between the tip and the sample, and via this impedance you get such important parameters as dielectric constant and carrier density. And SECM has a related mode, which is called scanning capacitance or SECM, which is measuring just the capacitance part of the microwave impedance, and we will talk about the differences between these two modes later. And the last but not least is the scanning electrochemical microscopy or SECM, which is a bit special here because while it is a measurement of current in liquid, but the whole experiment is a part of an electrochemical reaction which is happening at the surface of the sample in the vicinity of the tip. Alright, so now we know the modes that we are going to be talking about today, but what these modes could be useful for? What are the areas of applications? Now, intuitively, you can expect that the electrical properties of materials are important to electronics and microelectronics industry, which are mostly based on traditional semiconductors. Now, here we can also include piezo actuators and data storage devices, so you study piezoelectrics and magnetic materials. And now the 2D materials recently came into play, and some of those are already used in modern transistors. You wouldn't believe it, but TSMC already demonstrated a transistor channel made from moly disulfide. That's the 1 nanometer technology, what they call it. Also the green energy production, such as solar cells, the perovskites research. So then it comes to the energy storage, so the properties of materials used in batteries become important. And when we talk about batteries, there is also electrolyte, so the electrochemistry is also important here. And last but not least, the dielectrics. We don't usually think of dielectrics as electric materials, but they are extremely important because they separate and mechanically support the conductors and semiconductors. And their dielectric strength and also microwave properties become very important too. And the information we get from all these electrical measurements, it's all listed here in the second column. It's basically all the electrical properties you can think of, plus the material or structural quality of materials and devices. Let's start with the conducting AFM as the most basic electrical measurement. The setup of the experiment is rather simple. You have a tip in contact with the sample surface, you apply a voltage to the tip or to the sample, and you measure current flow in between the tip and the sample. With this, you can measure currents in pretty much any material, even in dielectric. The only question is what kind of amplifier you would need to use to properly detect your current. Your choice of the amplifier depends basically on two things. What is the current range you would like to image, and what is the minimum current you could live with? When scanning the sample, you get these conductivity or resistance maps. And you can also stop your tip at a certain location in your sample and record an IV curve there, which is a current voltage characteristics. This can give you insights in what type of conductivity you are dealing with. Is it metallic, is it semiconductor, or more towards a dielectric material? As I already said, there are different amplifier designs for different current ranges. The very simple one is the linear amplifier with a set of 2 or 3 feedback resistors. This would give you a current measurement somewhere between 1 picoamp and 1 microamp. And to get the best sensitivity at the current of your interest, you would have to switch the feedback resistor. Sometimes you need to measure a very large range of currents in one image. The linear amplifier cannot offer you a large range because it inevitably saturates. Even if the amplifier doesn't saturate, often there are well-conducting and poorly conducting regions inside the same sample area. In that case, your current image might be like it is black and white without showing the transitional colors. And to highlight these transitions, it would be better off if it is shown on a logarithmic scale. This is when the logarithmic amplifier becomes useful. In a logarithmic amplifier, the feedback resistor is replaced by a diode, and the function of the output voltage with the current is not linear but logarithmic. This kind of amplifier provides the largest possible range of current measurement without switching ranges. And historically, this measurement has been used in semiconductor industry to estimate dopant density in semiconductors, where it could go through many orders of magnitude change in one device. The method was called spread and resistance analysis, and this is why the conducting AFM with the logarithmic amplifier is conventionally called the scanning spread and resistance microscopy, or SSRM. Now, there is another amplifier design which is fundamentally not very different from the linear amplifier, but it is using much larger feedback resistor to detect smaller currents. In this design, the capacitance in parallel to the feedback resistor becomes important, as well as much better shielding and cabling. And when you measure in femtoampere currents, a bending of a dielectric in the cable could produce enough signal which is not the tip current. So these three amplifier designs would get you covered for any conductivity experiment one can imagine. On this slide, I have collected a few CIFM images to show you what kind of data you could expect from a conducting AFM. On the left, I have two samples imaged with the linear amplifier, and on the right, the two samples imaged with the logarithmic amplifier. One measurement out of four is actually the same sample, which is at indium tin oxide, or ITO. It is a conducting oxide and it is transparent. It is often used in displays or anywhere else you would like to have a transparent electrical contact. In both cases, you see the collection of bright dots, which are the metallic regions in this oxide. And with the scanning spread and resistance, you can see that the total current range is 60 times bigger than the one of the linear CIFM image. But also you see more shades between the grains where the small currents are flowing. And in the left image taken with the linear amplifier, these regions are just black. One of the other two samples that we have measured here is the interconnect structure, measured with the linear amplifier. You could see different resistances of different metallic contacts in this structure. And the last sample is the semiconductor SECM calibration sample with a range of dopant densities between 4 to the 15 and 1 to the 20 of atoms per cubic centimeter. Now this sample is obviously best measured with a logarithmic amplifier because of the large current range here of 16 microamps. To finalize the topic of conducting measurements, I would like to briefly discuss the scanning tunneling microscopy, or STM. In the STM, the tunneling current between the tip and the sample is used to control the tip height above the sample. And the distance between the tip and the sample for the tunneling current to exist usually corresponds to a strong attractive regime. Therefore, STM is usually done with stiff STM tips. Because of the stiffness and relatively strong tunneling currents close to nanoamperes, it is relatively easy to reach atomic resolution in such a measurement. When you measure current voltage characteristic in STM at a fixed height above the surface, you measure the local density of states in this material. This makes the STM an important tool in the material science toolbox.
In KPFM, you measure surface potential maps. It's a dynamic mode, which means that the tip is oscillating, and at the same time you're applying an AC electrical field to the sample, between the sample and the probe. The basic idea is that between the tip and the sample there is an electrostatic field due to the applied voltage between the two and the difference in Fermi energy. This field has an associated, basically it's a capacitor and has an associated energy. When you calculate the gradient of this energy, it turns out that it produces a force that depends on the voltage applied and the gradient in the capacitance. So how you detect this force, or how you detect this voltage between the tip and the sample? Well, you add an AC signal which combines with the applied DC voltage and the contact potential difference between the tip and the sample. When you put this into the force, it turns out that it appears several different terms which are varying at different frequencies. You have a DC term that is constant. You have a first harmonic which oscillates at the same frequency as you exciting signal. You have a second harmonic, and you can keep expanding this to have even higher terms. Depending if, for instance, you consider the capacitance to be constant or it varies. So how do you use this for measuring the difference in contact potential? Well, for instance, if we look at the first harmonic, this harmonic tends to zero, disappears when the voltage applied to your tip matches the voltage of the contact potential difference. So this is a way of creating a feedback loop to detect this signal. Most basic setup for KPFM involves two feedback loops with two lock-ins. In the first feedback loop, is for the mechanical excitation and tracking of the surface. So you are typically using the resonance frequency or your cantilever. And this is used to control the actuator that lifts and lowers the probe to track the surface. Of course, it uses the laser for reading up the signal. Second loop is the one that takes care of the electrical signal and also uses the detector, the photodetector, to read out, and it basically applies a voltage, an AC signal plus a DC component to either the tip or the sample. Now, over the years, people has developed different ways of measuring this surface potential. Is the different KPFM modes. If you're using, for instance, amplitude modulation, and you're using at the same frequency as your mechanical excitation, but you're using in a second pass, you have amplitude modulated lift mode. So according to this diagram, you are exciting mechanically the probe at its resonance and detecting this at its resonance as well. And electrically, you're using the same frequency for detection and readout. Another method, for instance, is amplitude modulated at the second harmonic. In this case, you use the first harmonic for topographical measurements, so oscillation of the tip, and you use the second harmonic for electrical readout. Other methods, for instance, more interesting because they achieve higher resolution, are the frequency modulated sidebands. So in this case, you excite with a low frequency electrical signal, typically 2, 3, 4 kilohertz, and this excitation at low frequency creates oscillations around the resonant frequency of the tip, and you use the amplitude of those oscillations to find out how much voltage you need to apply. Or heterodyne KPFM, for instance, here you are exciting you're exciting electrically the cantilever at a frequency that is the subtraction of a first and second harmonic, and then you're detecting this electrical effect at the second harmonic. Each of the method has an advantage or disadvantage against the other, and it's not clear unless you specify very well the sample which one might be better priori. Why is that? Okay, so for instance, here we have an interaction volume. So it's telling us, depending on the distance between the cantilever and the surface, which part of the probe interacts or contributes more to the electrical signal. So we can see, for instance, in an amplitude modulated technique, the contribution of the cantilever is significant, when we are at some very far away, but it's also when we are very close. And it's the contribution of the apex is the only one that increases. But at very close distances, we have more or less equal contributions of all of them. This means that your resolution is not going to be very good in amplitude modulated. On frequency modulated, for instance, down here, you can see that the cantilever contribution is negligible. It's almost disappear when you come close to the surface. There is still some contribution of the cone, but it decays very quickly. And most of the contribution when you're close comes from the apex. This means that you're going to have very good resolution with heterodyne KPFM. And in these images here, you can see the differences. So for instance, between amplitude and amplitude modulated at second harmonic, there is already a difference in resolution. You can see more detail. But when you use heterodyne KPFM, you can see even more detail. Why or in which situations it might not be more advantage to use these techniques? Well, if you have a probe with very high Q factor, for instance, it might not have too much of signal at the second harmonic because it might be too stiff. Or for instance, if you use a technique that involves some sort of excitation at a mechanical frequency or one of the harmonics of the mechanical resonance, you might induce defects in the topography tracking. So this is why in KPFM sometimes you need to choose between which technique you want to use, depending if you favor, let's say, artifacts or what is more important to you, artifacts or resolution. And this is why in most of the cases it's interesting to switch between two of the techniques to see if there is a variation between the results and how large is that variation. Magnetic force microscopy, or MFM, is a technique used to measure the stray magnetic field above the sample. It uses magnetically coated probes and is typically a two-pass technique. The reasoning behind this is that your van der Waals forces are very strong close to the surface, but they decay very quickly, while electrical and magnetic fields tend to decay more slowly. So if you move your tip away from the surface, all the interaction you're going to have is the electrical or magnetic. And if you can, for some reason, consider that there is no electrical or that it is uniform, then all you measure is the magnetic signal. It's a dynamic mode technique, of course, and in terms of the coating of the probes, because the coating is going to affect quite a lot your resolution and the amplitude you're going to obtain from your sample, and the generation of tip artifacts or not in your images. There is several types of coating. For instance, if you think of the tip as one magnet and the sample as another, if you have two strong magnets, you're going to produce a strong signal. But maybe one is going to affect the other and move it or turn it upside down. So maybe you want to reduce the amplitude of one, but then maybe that one is going to move, or maybe now the signal is too small, so you need to balance. So for this, typically you have low momentum probes, standard or high momentum. This applies to how strong is the stray field of your probe. And you also have probes with low and high coercivity. This is how they respond to magnetic fields. So a probe with low coercivity is going to flip the magnetization with small fields. A probe with high coercivity is going to remain the same for a long time. Typically, these two properties are linked. So it's not easy to find a probe with high momentum and low coercivity, and also the opposite. Also, they are linked with the resolution you're going to obtain. Typical samples for MFM, for instance, electrical steel here, where you can see 3 grains, where the steel is oriented in different directions and marked now the boundary between the grains. And you can see the magnetic textures are different between the different grains. For instance, hard disk drive here, where you can see the bit encoded information in the sample. And also nanostructured devices or materials. Usually, experiments experiments are interested in understanding the behavior of magnetic samples in the presence of an applied magnetic field. That's why in NanoSurf we have this option, which is a variable magnetic field holder, which can apply an in-plane or an out-of-plane field and allow us to take measure magnetization at different applied fields. In this video, for instance, we can see a piece of electrical steel, and we can see how domains change as we vary the applied magnetic field. In this case, we see that the magnetization in the different grains evolves in time. We can see very clearly, or more clearly than with static measurements, the boundaries between the different domains. And we can see probably the presence of defects or high concentration of probably iron in this case. The last thing to mention is that typically MFM is a technique that is combined with KPFM, because the presence of electrical fields can hide or can create artifacts in magnetic force images. So in this sample here, we have islands of a magnetic material, and the image on the middle shows the surface potential, and it shows that these type of stars in the middle, these ones, have a higher charge or higher potential than the structures around them, and different potential at the background, of course. We can see also some places where probably, if this is contamination, probably the contamination is creating an accumulation of charge. So if we take the MFM image without compensating the surface potential, we will obtain artifacts that hide the real MFM signal. This one here is the MFM signal taken with a compensation, where we can see all the fine details that arise from this structure. I have to add that the MFM is a technique that is very prone to artifacts due to for instance, the most common one is scanning too far away or too close to the surface. In those cases, the surface topography appears convoluted with MFM. The second most common artifact is due to interaction between the magnetization of the sample and the magnetization of the tip. And here in this image, we can see 2 clear examples of that. So if you notice this here and that there, these horizontal lines parallel to the scan direction, they are very likely indicating that the magnetization of the sample is being affected by the tip, by the magnetic tip moving close to it. This is why MFM is usually recommended to perform it with different probes, low and high momentum, different magnetic fields to see if domains change, and usually with electrostatic compensation with some of the KPFM modes we saw before.
The piezoelectric force microscopy, or PFM, is measuring the piezoelectric response of the sample to the applied voltage between the tip and the sample. This response is usually very small, of order of some picometers, and it would be very difficult to measure it in a DC deflection mode. That is why in such a measurement, while the tip is scanned in contact with the sample, an AC voltage is applied at a certain frequency, and the tip deflection is also measured at the same frequency with a lock-in amplifier. If you have piezoelectric domains in the sample, let's say oriented in and out of plane, you would see the similar signal amplitude for both domain orientations, but the signal phase will undergo a 180 degrees flip, and the domain walls would show as dips in signal amplitude. As I already mentioned, the PFM signals are small. Also, they can be easily confused with electrostatic signals, which would come from the cantilever movement under the electrostatic force, which is coming from the applied AC voltage. So apart from using the lock-in, there are various ways to boost your PFM signal, and there are different techniques to actually do the PFM measurement. Let's look at these techniques a bit more in details. The very basic PFM measurement is done with a lock-in frequency below the tip resonance. This is called the off-resonance PFM measurement. Such measurement is the least sensitive, but still you can yield good results in samples with strong signal, as for example here in the case of lithium niobide sample, which is a typical PFM test sample. If your signal is small, you can select the contact resonance frequency as the working frequency for your lock-in. This would give you some signal amplification due to the mechanical resonance. This frequency is typically 6 to 8 times the free resonant frequency of your cantilever. Here in the top right is an example of a contact resonance curve measured for top 100 cantilever. And here below is the phase image of a PZT sample measured with a PFM at the contact resonance. If you want to polarize your PFM sample, very often you need voltages higher than 10 volts, which one could get from a standard digital analog converter. In that case, one could use voltage amplifiers with output voltages going to 100 or 200 volts. This is what normally is called a high voltage PFM. When operating PFM with high voltages, there are certain safety measures that need to be taken to prevent accidents. Those safety measures are usually different interlocks to prevent human access to the high voltage area during the measurement. And here in the bottom right is the PFM image of the PVDF film polarized with 40 volt tip voltage. Now I would like to discuss a very useful PFM mode which is not an imaging mode. It is called the switching spectroscopy PFM. In the same way as IV curves, which are only measured in certain points of a conducting sample, the switching spectroscopy is also measured in a few points of a piezoelectric sample. In the switching spectroscopy measurement, the voltage undergoes a complex ramp with both DC and AC voltages added together. While the AC voltage has constant small amplitude on top of the DC voltage and is being used for the detection of piezoelectric response, the DC voltage is shaped in the form of long pulses of monotonously increasing and decreasing amplitudes, forming this sawtooth shaped voltage ramp of DC voltage in on and off state. What happens is, first you polarize the sample in one direction with a large DC pulse, then you turn the voltage off and probe the piezoelectric effect. Then you make pulse of a small amplitude, turn it off, and again probe the piezo effect. Then at some point you would start reversing the polarization of your sample and with these DC voltage pulses, and this is when the signal amplitude would drop and the phase would experience the 180 degrees shift. Then you repeat the whole sequence in a different direction, and the resulting PFM signal curve versus the DC voltage of the pulses, because of its shape, it's called the butterfly curve. This curve is giving you an important information about switching voltage in your sample, which is required to reverse the domain polarization. And in this particular sample, it is of the order of the minus 22 and say 18 volts. The last PFM mode I would like to discuss today is the dual frequency resonance tracking, or DFRT PFM. The contact resonance PFM, while being very helpful in amplifying small signals, has one disadvantage. The contact resonance frequency depends on local sample stiffness and the force applied to the tip. Therefore, it can change while scanning. making this very inconvenient for this amplification to be used. To make it convenient, we need a method to track this resonance. The DFRT is exactly such a method. To track the frequency of contact resonance, one could excite the sample with additional frequencies on each side of the resonance peak, on the left and on the right, such that the signals at these frequencies have the same amplitudes. Now, if the resonance shifts to one and another direction, the amplitudes of the signal at these frequencies would immediately become unequal. One could build a PID controller that would adjust the two frequencies to minimize the difference in signal amplitudes, and in that way effectively tracking the contact resonance. This PFM method is especially useful for thin films. Now we're slowly turning towards more complex electrical modes such as scanning capacitance and scanning microwave microscopy. From the name of it, the scanning capacitance is obviously measuring the capacitance between the tip and the sample, meaning you have to have a conducting or semiconducting sample, an isolator on the surface, and a conducting tip to build the capacitance in question. If your sample itself is metallic, this method is not very useful because there won't be much capacitance change if you scan across it. However, in semiconductors, there is the so-called depletion capacitance, which depends on the carrier density, and this can be changed in large ranges by varying dopant levels or gate voltages, and this one would give a detectable contrast in scanning capacitance measurement. The experiment design is rather old. The microwave frequency is sent to an antenna, which is coupled to a quarter wave resonator, and the resonator is coupled to the receiver. The tip is connected to the resonator, and together with the voltage controlled capacitors or varactor diode would define the resonant frequency of this quarter wave resonator. The working point and frequency would be on the linear part of the resonance peak, and a small change in the tip sample capacitance would result in the change of the resonance of this quarter wave resonator, and this would show as a DC signal on the detector. Older designs weren't that sensitive, and therefore the capacitance was modulated by applying the oscillating gate voltage to the sample, and the DC-dV signal was measured. By this day, the DC-dV measurement is a standard capacitance measurement, because the phase of this signal bears the information about the carrier type P or N, holes or electrons, because they have different effective masses. Here below is the example of the scanning capacitance image showing two different dopant regions, P and N, and the depletion region between them. Scanning microwave microscopy, or SMM, is yet another AFM technique that is using microwaves to probe electromagnetic properties in samples. Unlike the scanning capacitance, which is a kind of transmission measurement, the scanning microwave is the microwave reflection measurement. The design of the SMM experiment is shown on the left of the slide. The microwave receiver and the transmitter are working on the same port, and the microwave radiation travels from this port through a matching network towards the tip. At the tip sample interface, the microwave is being reflected and travels back via the same transmission line to the receiver. The reflection coefficient is then recorded as a function of a tip position. The reflection coefficient itself, or S11 parameter, is a complex number, which could be represented by its amplitude and phase, or by its real and imaginary parts. The relation between the real and imaginary parts of the S11 and physical quantities is easier to understand from this formula, where the real part is associated with the resistance and the imaginary part is carrying the information about the capacitance between the tip and the sample. Because the phase of the S11 is not well defined, the correct separation between the resistance and the capacitance is only possible if there is a reference measurement where those values are well defined. The range of materials that could be studied with the SMM is diverse. The semiconductors, of course, but also metals and dielectrics. And because the microwave penetrates to some depth below the surface, it can also be used for subsurface imaging. As such, this technique is extremely valuable for imaging defects in electronic devices and for failure analysis in semiconductors. In the S11 measurement, the excitation and the detection are done at the same frequency. There is another mode of SMM which is similar to the DC-dV measurement of scanning capacitance, which is called DS-dV measurement. In the DS-dV measurement, which works only in semiconductors, the depletion capacitance of a semiconductor sample is being modulated by a gate voltage, and this modulation modulates the S11 parameter. This gives rise to the sideband peaks at the frequency spectrum of the S11 parameter. And if instead of the intensity of the main peak, we would record the intensity of the sideband peak, we would have the measurement which is very similar to the DCDV measurement. As I mentioned earlier, this measurement is a standard measurement for semiconductor industry, where it is being used for dopant density profiling and determination of the type of dopants and or P, which is clearly visible in the phase of DSDV measurement. Because of different effective masses of electrons and holes, the phase of the DSDV measurement would have a clear phase flip when switching from one dopant type to another. The last electrical mode which I would like to discuss today is the scanning electrochemical microscopy, or SECM, which is becoming increasingly popular mainly because of the battery research, but also because of interest in materials that could facilitate splitting water into hydrogen and oxygen. In the scanning electrochemical microscopy, the tip current is being measured in an electrochemical cell, where a redox reaction is taking place in the presence of a conducting tip and a sample with especially varying reactivity. The reduction reaction is a gain of an electron by an oxidant, and the oxidation is a loss of an electron by a reducing fraction. A crucial part of the SECM is the electrochemical cell, which consists of a closed volume in which the chemical reaction is taking place. There are several electrical connections from this volume to the outside. These connections lead to the device called bipotentiostat. This device allows for the electrical control and measurement of the reaction. The reference electrode is measuring the electrical potential of the solution, and the tip voltage is applied relatively to this reference electrode. And the counter electrode is keeping the potential of the reference electrode constant. This is necessary because there is an ongoing reaction in the cell, and without the counter electrode, the potential of the reference electrode would constantly change. The result of the SECM measurement is, of course, a map of reactive areas in the sample, and also an analog of an IV curves. In a conducting AFM, there are so-called CV curves, where the CV stands for cyclic voltammetry. Now, the understanding of the simple CV curve and all the processes that cause the shape of it is outside of the scope of this webinar. Here I would simply say that it bears important information about the speed of the reaction and the relative concentrations of the oxidants and the reducers in the solution. And this information is crucial for the understanding of this chemical reaction on the microscopic level. For the SECM, it is important that the surface of the tip which is participated in the reaction is kept as small as possible. Therefore, SECM tips are insulated with only a small opening at the end of the tip, through which the current can flow into the solution. Here in this photo, you could see a conducting tip which is insulated with a polymer, and only a small opening right at the very end of the tip is open for the current. And as I have already mentioned, you need an electrochemistry cell to control the flow of the reaction. To finalize this webinar about electrical modes, I would like to mention that all electrical measurements can benefit a lot when they are made inside of a controlled environment. First, many surfaces oxidize. This is true for silicon, for example, and a bit less for 3-5 semiconductors. Metals, and especially magnetic alloys, normally oxidize very fast, so oxygen is often a problem. Second, the humidity in the atmosphere would create a layer of water on the surface of the sample, but also on the surface of the tip, making calibrated measurements difficult. Water can help you to make a better contact between the tip and the sample, but then it becomes a variable in your calculation, and the humidity can vary over the time. So your measurements would lack reproducibility. 2D materials and van der Waals heterostructures are showing much better results when produced inside of a controlled atmosphere too. To fight oxygen and water, it has become a convention to use a glove box. This device isolates your whole system from the ambient atmosphere and helps you a lot to make reproducible electrical measurements. The real estate inside a glove box is limited and expensive. And also opening and closing the box is a time-consuming process. So a small FM that would fit an introduction chamber and doesn't take all the floor space inside of the glove box is very convenient. I would like to close this webinar by showing again the first slide, with a little bit extended set of electrical modes. We have learned today about the 6 main electrical modes, and we have learned that many of them consist of a rather family of measurements, depending on the samples which need to be studied, the information that needs to be extracted, the requirements to the measurement sensitivity, and both electrical and spatial resolutions. With that, me and Hector would like to thank you for your attention and welcome your questions.